Okay, guys, geometric sequences. I'm on the clock because in like 15 minutes I got a study hall coming in here, and I swear if I'm not done with this video, I'm going to rip somebody's head off. Just saying. You've been warned. All right. So, Unit 4, we talked about sequences, and it's just the specific numbers in a particular order. So then we specifically talked about arithmetic sequences, where each successive number, meaning each number in the list, next number in the list, was generated by adding the same quantity. So it says, let's talk about this warm-up. So a little review here. An arithmetic sequence is defined recursively. So if you remember, recursively relies on the term before in order to generate the next terms. So we've got a sub 1, and here's our rule. So our rule says to get the next term in line, we've got to take the term before, that's the term before that a sub n minus 1, and then we add 3 to each successive term. So it says find the next 3 terms. So a sub 2 would take the term before and add 3, which is 8. A sub 3 would have to take the term before, which is 8, and add the 3 and get 11. And then a sub 4 takes the term before and adds 3, and we get 14. So now it says find the value of a sub 20 without listing out all 20 terms. So if you sit and think about that, a sub 20 is, we've got our 5 that we started with, our initial term, and we're adding how many more 3's? We're adding 19 more 3's. Okay, so 19 more 3's. So if we do that calculation, we end up with 62. Okay, that would be the explicit definition. Remember, helps us jump to a term. The recursive definition has that limitation because it relies on the term before. The explicit lets you jump to a term. Okay, say I wanted a sub 20. Or I'm not a sub 20, duh, we just found a sub 20. What if I wanted a sub 100? Okay, it would allow us to jump to a sub 100 without listing out all the other terms. So it says clearly an arithmetic sequence has linear characteristics. The arithmetic sequence is an example of a discrete linear function. Remember we talked about discrete, it's not everything in between, it's distinct points. So the exponential has their own discrete version called the geometric sequence. And let's talk about the recursive definition for that. So again, you need your first term, your a sub 1, and then to generate terms from that is you take the term before and you multiply it by a constant, and that constant is r, and it's that our common ratio. Okay. So let's look at some quick examples here. And they're telling you that these are geometric sequences, and they want you to find the common ratio, meaning find the multiplier, and then give the next 2 terms. So this one's not too bad. To go from 2 to 6 and then 6 to 18, we know our common multiplier is 3. So then if we continued multiply each previous term by 3, we end up with those. Next one, how would I go from 4 to negative 20? What am I multiplying by? I'm multiplying by negative 5. Does that hold true from here to here? So negative 20 times negative 5 truly is 100. Multiply 100 by negative 5, and then multiply negative 500 by negative 5. And that's what you end up with. What about this one? We're going from 16 to 8 and to 4. You're thinking, well, I'm dividing by 2. Well, that's true. But the geometric sequence relies on multiplying by a constant. So what is the same thing as dividing by 2? You're multiplying by 1/2. So my common ratio is 1/2. So we're taking half each time to generate those terms. Okay. So let's see about this. Consider the geometric sequence given by this recursive rule. So my first term is 3, And my rule says, take the term before. Remember, this represents, that's just function notation to represent the term before, and multiply the term before by 2. That 2 is my common ratio. Okay? So it says find B2, B3, B4, and write each as an extended product so we can see a pattern start to evolve. All right? So B2 is take the term before, okay, or the first term, and multiply it by 2, and we get 6. So B3, still going to have that first term, okay, that 3, and multiply by 2, but we got to multiply by 2 again to generate that term, and we end up with 12. So then B4, first term, and 2 times 2, because that is all encompassing a piece of 3, but we got to multiply by 2 again. So we end up with 24. So hopefully you're starting to see a pattern that's being generated here. So then B sub 10, or B of 10, would be 3 times 2 to the what power? B of 10. Okay? You've got to the 9th power, right? So if you sit and think back here, this was 2 to the 1st power. Well, this one was 2 to the 2nd power. And this one is 2 to the 3rd power. It's always one less than the term number that you're trying to find. So if we're trying to find the 10th term, it's going to be raised to the essentially 10 minus 1, okay, or the 9th power, and that would give us a value of 1536 for B of 10. And then what about B of 20? Again, first term times the common ratio to the what power? If we're trying to find the 20th term, we're going to raise it to the 19th, or the n minus 1, okay, the 20 minus 1. So that ends up getting 1,572,864. Flipping the page. All right, let's talk about this. I love this example. I talked about it briefly in class. It says, you have just won a very strange lottery. The lottery promises to give you money each day for a 30-day month based on one of two options. Okay, so it says option 1, you can receive $1,000 on the first day, $2,000 on the second, $3,000 on the third. This is an arithmetic sequence. Okay, you're adding $1,000 each day. But option 2 says you can receive a penny on the first day, 2 on the second, 4 on the third, 8 on the fourth, and this is a geometric sequence. Which option would you pick? Okay, let's sit and think. It says, of the two options, which would result in a larger payoff on the 30th day only? Okay, on the 30th day. Show work that supports your answer. Which one would you rather pick? So, let's talk. So, option 1. My first term is $1,000 on the first day. So then on the 30th day, I take my first term, 1,000, but then I'm adding how many thousands after that? You should say to yourself, okay, I'm adding 29 of them. Okay? So remember, it's times n minus 1. So we end up with, on that 30th day, and you probably could have come up with that idea knowing that there were 30 days in the month of $1,000 each day. $30,000. Okay? Well, what about option 2? Okay. So it says, of the two options, which would result in a larger payoff on the 30th day? The 30th day, how much money would you get? Okay? So we know that on the first day we're getting a penny. So then what's going to happen on the 30th day? So we've got that penny, right, as our first amount. And then what's happening? Okay, it's doubling. Okay, as if you can see, it went to 2 cents, then to 4 cents, then to 8 cents. So we're doubling, or we're multiplying by 2. So we're going to multiply, 2 is my multiplier, my common ratio. And on the 30th day, I'm going to raise that to the 30 minus 1, okay? Or I'm multiplying 0.01, or that 1 penny, by 2 how many times? 29 times. So if you sit and do that calculation, holy smokes, 5,368,709.12 just on the 30th day. Okay, the 30th day, you're getting that much money in one day. Okay? Crazy. Crazy, crazy. So you could see how the exponential grows so rapidly and will surpass that linear function. So it says graphs of geometric sequences will look familiar because they are discrete exponential functions. What do we mean by that? We talked about it in the beginning, and we did talk about it when we talked about graphing the arithmetic sequences. So we've got our definition, we've got our first term, and then we've got our recursive rule. It says list and plot the first 6 terms on the grid below. So my first term is 16, and then my second term, and it tells me to take and multiply the term before by a half. So my common ratio is 1/2. So I get 8, and I get 4, 2, 1, 1/2. Okay? So this is exponential decay, all right, a little review. We've got decay because that multiplier, that common ratio, is a number between 0 and 1. So if we were to plot these, because remember, it's a sequence. It's a list of numbers. It's not continuous. So we don't have everything else in between. Right? So we have my 1, 16, 2, 8, 1, 2, 3, 4, 5, 6, 7, 8, right? 3, 4, 4, 2, 5, 1, and then 6, 1/2. Okay, it's discrete. It's not continuous. We're not going to connect the dots because we don't have everything that's in between. It's just these discrete numbers. Holy smokes, I made it with a minute to spare before that study hall comes in. Everything's all good. Nice job, guys.